Now, the elementary reaction, which is molecular level reaction, one molecule of CO plus one molecule of OH giving one molecule of CO2 plus one atom of H. That is the way we read this. Now, molecule of this reaction, it's a reversible reaction, you can see these two arrows. Then molecularity of the reaction is 2. That means 2 molecules are used for the reaction to occur. This reaction will take place in one step. So, okay, what is one step? In a particular collision between say CO and OH, one bond can break and one bond can form. That will lead to the production of CO2 and H. Okay. So, that means if CO and OH collide with each other with proper force, which is called necessary force, and proper orientation, okay, H side hitting O side and so on, then one bond will break and one bond will form simultaneously, producing CO2 and H. So, this is possible. So, it can occur in one step, but the global reaction cannot occur in one step. So, the collision between the CO and OH molecule with necessary force and proper orientation will help in break in bond and form new bonds and produce the products. Similarly, reverse reaction also will take place. Again, CO2 and H will collide to form CO and OH. So, at a given temperature and pressure, there will be some amount of CO, OH, CO2 and H. The particular condition will favor forward or reverse reaction. So, that again equilibrium will tell us. The amounts of CO, OH, CO2 and H present are dependent on the equilibrium constant at a given temperature and pressure. We have already seen this. Now, law of mass action. Now, first of all, we have seen that molecularity of the particular reaction what I have shown is 2. Several reactions if you take, molecularity will be around 2 only. Why? Because the probability of 2 molecules colliding and forming products are very, very high. So, we need a probability factor also for this then, correct? So, the energy of collision, orientation of collision and probability that the collision will lead to a possible reaction. Okay. So, these 3 are important. So, 2 molecules colliding are very often occurable, but molecule of 3 only few occurrences are there. Say 5 or 6 reactions are there. Dissociation reaction, CO2 giving CO plus half O2 or O. In the forward side reaction, you can say the molecularity is 1. One molecule of CO2 breaks and so on. So, now what is rate of reaction? It is defined by law of mass action. What it says? The rate of a chemical reaction is proportional to the concentration of the reacting species, that is all. So, when you say rate of a chemical reaction is proportional to the concentration of the fuel and concentration of the oxygen or oxidizer species. That is what it says, and there is a proportionality here, say K. Now, this concentration has to be raised to appropriate powers. I have given N1 and N2 for example here. Okay. So, fuel concentration is higher, reaction rate will be higher. When oxygen concentration is higher, it will, but once the fuel and oxygen deplete, the reaction will go down. Okay. Now, what is this K? Normally, when I say something is proportional to something else, this will be the constant of proportionality. But actually speaking, this is a strong function of temperature. We will see that in a little bit. Okay. So, this statement, what I have written mathematically, is called law of mass action. Okay. So, with this statement, see obviously what this statement says is The chemical reaction is proportional to the concentration of reacting species, and the constant of proportionality itself is a strong function of temperature. That's what we are going to use it for defining the rate of reaction. We will do it in a little bit. Now, the N1 and N2 can be integers or decimal numbers based upon what type of reaction we are going to consider. Whether it is elementary reaction where N1 and N2 will be integers, if it is a global reaction, they will be decimals. Now, one more thing, molecularity we have seen, one more thing is the order of a reaction. What is the order of reaction? Once I define the reaction like this, then the order of the reaction is N1 plus N2. That's all. Sum of the powers of the concentrations of the reactants participating in the rate equation. This is called rate equation. So, N1 plus N2 is the overall order of the reaction. So, if you take CO plus OH reaction, I will say reaction rate will be equal to some K times concentration of CO, concentration of OH raised to the power 1 because that is a molecular level reaction only. So, here the order is 2, order will be equal to 2, which is equal to molecularity. So, for elementary reactions, order and molecularity will be the same. Yeah, so now that is what exactly I am trying to specify here. Order and molecularity of an elementary reaction have the same value. So, again considering the same example of CO plus OH giving reversibly CO2 and H, the molecularity is already seen as 2, CO one molecule and OH another molecule. So, molecularity is this. So, the rate of the forward reaction is given as what? The rate at which CO concentration decreases. So, when I say omega dot triple dash, that will be equal to the rate at which the concentration of CO2 decreases with time. Actually, it's a negative value because CO2 concentration decreases. So, it has a unit of what? Kilomole per meter cube, that is concentration, divided by second. That is the rate of the reaction. If you use the molecular weight, you can make it as kg per meter cube second. So, now this is equal to some coefficient into CO power 1 because this reaction, the value of the molecules itself is used as the power. So, CO power 1, OH power 1. So, the order of the reaction will be 1 plus 1, which is same as the molecularity. Okay. So, CO within square brackets is the concentration of CO. Similarly, OH within square brackets is the concentration of OH. The rate at which reaction takes place is the rate at which concentration of CO, actually since it is a reactant for the forward reaction, it is a reactant, it decreases with time. So, once CO decreases in a particular rate, OH also should decrease in the particular rate. Correct. So, the same rate OH also will decrease with time. Now, coming to the product side, same rate CO2 and H also should increase. The concentration of CO2 and H also should increase. So, that means the reaction should be coupled, correct. So, we can say that when the forward reaction takes place, the rate at which the reactants deplete will be the rate at which the products are formed. Now, coming to the overall order, as I told you, the overall order is 2, molecularity is also 2. Now, we have already shown that for this reaction, the forward reaction rate is written as simply in a using law of mass action, K times CO2 power 1 OH power 1. But this K to determine is the value of K is not so easy. A lot of experiments have to be done. This is a constant of proportionality because we have said the rate of reaction is proportional to the concentrations. So, this is a constant of proportionality, but it is not a constant in fact. So, it is a rate coefficient which is a strong function of temperature, varies as a strong function of temperature. For elementary reaction, to determine the value of K, there is some basis, theoretical basis based on kinetic theory. But even then, experimental values are required for us to fit the curve. That is, fit an expression to calculate the value of K. We need experimental data also. So, what is the methodology to follow to get the value of K? So, first of all, we have to understand how the reaction takes place. For a successful occurrence of a chemical reaction, Arrhenius and Van't told that some conditions have to be satisfied. First of all, molecules which can react, they are called suitable molecules, should collide with each other. The collision must be of proper orientation. O atoms should collide. Then they should collide strongly. If it is only weak collision, nothing will happen. Strong collision should take place. That means both these molecules should be energetic enough to collide and break the bonds. So these are the conditions. Then the formation of bonds will occur simultaneously. So now when the reaction has to take place, so you see the energy level, you can say enthalpy also, versus the extent of reaction. The extent of reaction is nothing but the energy, this is the low extent, that is nothing, reaction has not even started here. Reactants remain as reactant, and you go to this point, you will see products are formed. So here the extent of reaction is complete. So I will say in a fraction it is 1, it will be 0. Now the reactants to products, so it's actually a exothermic reaction because the enthalpy of or the energy of the reactants are higher than that of the product. So it's an exothermic reaction. Hp minus Hr is negative. Now the reaction cannot straight away take place from the reactant energy level to the product energy level. It has to be, the reactants have to be taken to a higher energy level by supplying something called activation energy. Then it goes to a activated complex level. That means now the collision between CO and OH will be strong enough. They will be activated. Now they collide and form the products. They disintegrate to the products. Okay, so the energy of the reactant has to be increased to a level where they form a activated complex from which the products are formed subsequently. So in order to do that, I need to provide the activation energy. The difference in levels of the energy between the activated complex and the reactant, the original reactant's energy level is called activation energy. Now, proper oriented collision can be strong enough when it is having the activated energy supplied to this. But the probability that the collision will occur between CO and OH plus O atoms will collide, that depends on a factor called A. Again, please understand that this A is not, that is no theoretical thing to find the A. For EA at least we can do that. So there is nothing very theoretical to find the value of A, which is the factor that takes into account of orientation and probability that the collision will result in a chemical reaction. So now with this, the rate coefficient can be written as K. Now I am putting a function of temperature. This was actually given by Arrhenius, so it is called Arrhenius form of rate coefficient equation, where the factor A comes into play, where the probability and orientation aspects are taken into account. Then the activation energy has come into play, which is coupled with the temperature itself, and this term EA by RUT is within a exponent term. So that imparts the exponential dependence on the value of K with temperature. So this is the Arrhenius form of rate coefficient equation. Now In some cases, the temperature dependence will be still larger. In this case, the range of temperature at which the K value changes is larger. Then I also include one more term, that is the third term, T power m, which is going to bring in some more nonlinear temperature dependence other than the exponential dependence which already the Arrhenius rate equation has. So now Kt is written as A T power m exponential of minus Ea by RUT. Okay, so now combining this, I can write the rate equation. Reaction rate, as I told you, it is in kilomole per meter cube. Concentration as the unit of kilomole per meter cube divided by second equal to A. This A is also called pre-exponential factor because it is previous to the exponential term. So, or is called probability term. T power m E exponent of minus Ea by RUT and concentration of CO power 1 and OH power 1. So, that is the rate equation. So, the values of A, M, Ea, these are very important. So, this is the elementary reaction. So, there is no need to find the N1, N2 etc. because there will be only the number of molecules participating in the reaction. So, the values of A, M and Ea will be got for several reactions by chemists, and we will use that data to analyze the rate of reaction. Okay, now the forward reaction rate of this is written like this, as I told. Now, controlled experiments are done, which are done in isothermal conditions. So, I have a chamber which is maintained at a given temperature, say 800 Kelvin, 900 Kelvin, 1000, 2000 Kelvin, etc. And I put the reactants in this and try to ignite it, and the concentrations of the reactants CO and OH are measured as a function of time. Now, with this data, now this concentration variation is known to me. With this data, I can get this correct. Now, I will try to, because the rate at which CO depletes will be the rate at which OH also depletes. So, from that, I can get the value of A and Ea and M also if you want. So, this tremendous amount of uncertainty also will be there in these experiments. So, when you do this experimentally, the value of A and Ea will have uncertainty 30 to 40%. But okay, that is fine, because if you don't have this information also, we cannot even attempt to study the rate at which the reaction takes place. Now, what we do to reduce uncertainty is, once you determine the forward reaction rate Kf, I will find the reverse reaction rate in a thermodynamic point of analysis. See, for example, I will define what is called a Kc, equilibrium constant. Based on concentration, which is nothing but Kf divided by Kr. That's all. Do you understand? When I do this, then I can write, see, for example, forward reaction can be written as Kf times CO into OH. Reverse reaction rate is written as Kr times CO2 and H. So, when I say Kf by Kr, it will be COOH divided by CO2H. That is the ratio of the concentration. So, that is the equilibrium constant I get. And what I will do is, I will connect Kc with Kp. Kp we already seen, which is dependent on the delta G. So, you can refer any textbook to understand this. So, when I evaluate Kc as a function of Kp, then I can find the reverse reaction rate thermodynamically, measuring the forward reaction rate. Do you understand? So, that is the way I can reduce, because this thermodynamic is much accurate, so I can reduce the uncertainty in the overall reaction rate forward and backward by using the thermodynamics procedure. Okay, that's what I was trying to show you quickly. So the forward at equilibrium, what happens? The rate at which the forward reaction takes place will be equal to the rate at which the reverse reaction takes place. So what is forward reaction rate? Kf times concentration of CO into concentration, this is square bracket, concentration of OH will be equal to Kr times concentration of CO2 into concentration of H. So when I say Kc equal to Kf by Kr, it is CO2 concentration into H divided by CO into OH. So this is the expression I have. Now Kc, which is the equilibrium constant written in terms of concentrations of product and reactant, can be related to Kp, which is divided using the standard Gibbs function change. So by this I can calculate Kf or Kr. So that is the expression I have. Kf by this is actually Kb, backward reaction or reverse reaction. So Kb equal to Kr, just for you to remember. Okay, now so let us consider this equation here. A times capital A. So A is the number of moles, it's elementary reaction, so number of molecules of A, B is the number of molecules of species B, and so on. So I can write, generally you can say that A, B, C, D will be 1. So Kf by Kb or Kf by Kr will be equal to concentration of C power C, or concentration of C into concentration of D divided by concentration of A into concentration of B. So that is Kc. Now concentration itself is nothing but the number of moles, which is A here. That's what I put A, because I can also put 1. So I put number of molecules here in this case divided by V, which is nothing but Pa by RUT, which implies Kc can be written in terms of Pc, Pd, because the partial pressure, and connect that to Kp. That is the way you do this. So now P naught is the atmospheric pressure equal to 1 atmosphere, and Ru is the universal gas constant, and this is the temperature at which this reaction is at equilibrium. So if we connect Kp and Kc, I will get the values of the ratio of Kf by Kb or Kf by Kr, from which I can determine one of them, measure one of them and determine one of them. So I need not conduct experiments to measure the second one. Okay. So this is about the single reaction rate. Now let us have several reactions like this. So in a chain reaction, how to calculate? See, each reaction is reversible. There are 4 reactions, R1 to R4, all are reversible. Now for each I have put what is the forward reaction rate and reverse reaction rate, Kf1, Kr1 for reaction 1, Kf4, Kr4 for reaction 4, and so on. And these are some examples I have taken into account. So now how will you write the net reaction rate of a particular species? That's what we are trying to see here. See, for example, when you write a species conservation equation, okay, for example, I want to write the conservation equation for H2, then there will be a term in that which will tell you, which will actually is a source term, volumetric source term, which will indicate the net rate at which this particular species is formed or consumed. That is, the net rate of production or consumption of a species can be determined by understanding in what all of the reactions the particular species is present, and where it is formed and where it is consumed. Okay. So the net rate is found by considering the reactions in which the species is involved and taking into account of both forward and reaction rates. So let us go back and see the rate at which O2 changes with time. For that, in these 4 equations, I have to first understand O2 is present in reaction 1, reaction 2, then it is not present in reaction 3, but it is present in reaction 4, 4 reactions. So now out of 4 reactions, in 3 reactions it is present 1, 2 and 4. So, now again you understand where it is first produced. It is produced in the reverse reaction of 1, reverse reaction of 2 and the reverse reaction of 4, and obviously it is consumed in the forward reactions of 1, 2 and 4. So, now add the reaction rates at which it is formed. So, reverse reaction of 1, reverse reaction of 2 and reverse reaction of 4. In these 3 O2 is formed minus the reaction at which it is consumed is forward reaction of 1, forward reaction of 2 and forward, they subtract them. So, that will give you the net rate at which the O2 is produced or consumed. Similarly, for H atom, identify H actually is there in the first one, second one, third one and fourth. In all the 4 it is there. And now H is produced in forward reaction of 1, is consumed in the reverse reaction. H is produced in the reverse reaction of 2 and consumed in the forward and so on. So, you have to identify this where it is produced and consumed. Then you can write the equation like this. Considering all the 4 reactions, whether it is forward or reaction. For example, you see that the forward reaction H is produced in reaction 1, it is produced in reaction 3, but it is produced in the reverse reactions of 2 and 4. Similarly, consumed in the reverse reaction of 1 and 2, okay, actually be, yeah, correct, and the reverse reactions of 3 and forward reaction of 4. So, you have to understand this and write. So, this, when you do this, we will get the individual species net rate of production or consumption which is required in the species conservation equation. Okay, now we have seen so far the elementary reaction rates where reverse reaction is there. Again, experiments have to be done to find the rate coefficient. Now, let us consider the global reaction rate, in which let us consider the methane reaction itself. So, now I can do some experiments to find the reaction rate of a global reaction, just putting the some amount of methane and oxygen inside a chamber, isothermal chamber, and I now calculate the rate at which the methane decreases with time, and monitor the concentrations of the reactants CH4 and O2. Then I can get the values of A, EA, that is all. So, this if I do, I get the global reaction rate of this one step reaction, where the rate at which methane is consumed will be 2 times the, for example, 2 moles, when 1 mole of CH4 is consumed, 2 kilomoles of O2 is consumed, that you have to understand. Similarly, 2 kilomoles of H2O is produced and 1 kilomole of CO2 is produced. So, that we can write. So, once you determine this expression, I can write the species conservation equation source terms by using this particular expression itself. So, here the value of A, EA and the exponents M and N are obtained from careful experimental data, and in this case M and N will not be integers. For example, N can be 0.25, M can be 1.5 and so on. So, basically the order of this reaction M plus N varies from 1.7 to 2.2. So, again the average will be about 2, but you can see that it need not be an integer. So, this is about the global reaction rate. But one point to understand here is, if you get a mechanism with lot of elementary reaction, then that reaction mechanism can be used to analyze a premixed flame or a non-premixed flame or any type of flame for that instant. But if you take global reaction rate and find the values of A, EA, M and etc., this will work only for the particular experiment what you have done. If it is a premixed experiment or a premixed experiment or a premixed combustion experiment or a non-premixed combustion experiment, the values will be useful only for such particular such configuration. Okay, so for example, if I determine these values for a premixed combustion, then I can use it only for the premixed combustion. For non-premix, these values will vary, but global for elementary reaction mechanism what you get, that will be useful for predicting anything.